This is Research Jam number 12. We've made it to 7 this year. So last year we had 5, this year we had 7. That's why it's 12. Today we have 4 presenters. One presenter decided not to have is the presentation being recorded, so we turn that off. We will let that be an option in the future. So this recording part will start with our second presenter, Sharangan. Did I pronounce your name right?
Yeah, right.
Fine. Cool.
Thanks.
Yeah, you can get started.
Okay, so hello everyone. I am Sharangan from the Department of Computer Science and Engineering from the University of Moratuwa, Sri Lanka. Okay, so we work on the problem for OCR, optical character recognition, for the lower resource languages. Actually, in Sri Lanka, the language, the majority of the people are talking Sinhala and Tamil languages, but those are in worldwide, it's recognized as the lower resource languages. That means there are no large corpuses or large models for some OCR applications, or as well as any other type of ML or AI applications. So we identify those issues like there was no high resource, lower resource parallel corpuses for Tamil and Sinhala, as well as in most of the authors in India and Sri Lanka, they are trying to digitize the old Tamil and Sinhala storybooks. But in that case, they are facing some difficulties due to the legacy fonts usages. Like this, as you can see, this is a new form of this of the Tamil fonts. On the other side, this is the old fonts usages. So if you take an old Tamil book, the fonts are like this, the old form. But the current OCR models are well trained with the new form. So they always fail to detect such fonts. So we work on this problem for creating and fine-tuning the existing Tesseract OCR model for detecting such fonts and to improve the OCR performance on the lower resource languages such as Tamil and Sinhala. So in our training, the experiment phase, we carefully collected 10 fonts for each language, for 10 fonts for Tamil and 10 fonts for Sinhala. The second table is for Sinhala and the first table is for Tamil. So in this first column, you can see the original Tesseract's results on a test set that we carefully selected. Then the fine-tunes performance. So we significantly reduced the error rate from 6.03 to 2.01 in the character level error rate. So as you can see, other matrices are there. So we try to reduce the error rates in these languages for identifying the legacy fonts in the old Tamil books. So for this purpose, we collected the text from the old books and add the corresponding coordinates of the legacy fonts to the TIFF file. TIFF file means we, for the purpose of training, we need to create a TIFF versus text file for training our model. So for the TIFF file, we need to add the coordinates of the missing characters. So we carefully collected the coordinates of the legacy fonts and added to the TIFF file to train our model. So this is a sample rendering of the TIFF file using the JTextBox editor. So also we can use this editor to modify the overlapping of the different characters or side-by-side characters sometimes overlap when the model detects the character. So we can easily remove the overlapping and correct the coordinates using this editor. So consequently, we developed a pipeline for extracting the text and making them structures data from all Tamil books using this pipeline. So for our pipeline, we can take scanned documents or PDF. It means the embedded PDFs or images as an input. For the inside the input processor, we need to convert the PDFs into images. If it is image, we don't need any processing. But if it is PDF, we need to convert the PDFs into the images. Then we applied some pre-processing techniques in order to make the image clear. Sometimes we take or when we scan the images, it shows some shadows or background images, different colors. So we applied some different pre-processing techniques on the images and then apply our OCR model to get the extracted text. So this is the sample pipeline. Finally, we created a parallel document aligned parallel corpus using our pipeline. So for this purpose, in our Sri Lankan government, there is a problem in our parliament. The presenters are using their own native language. If we take a singular presenter, they always use singular language to present his ideas. So while the other language presenters are waiting for the translation. So there is no any live translation systems. So we carefully collected the papers presented during the parliament in order to create a machine translation system, because every domain has specific words. So if we need to create a machine translation system for a parliament, we need those data. So that's the reason we choose parliament website to get the PDFs. So we get the PDFs from the parliament website and use our pipeline to extract the text. So as a result, we end up with this parallel corpus. So this is the statics of the parallel corpus. So in our future work, we are trying to create a multilingual or machine translation system for Tamil and Sinhala in a live manner. So you can see this is a sample UI we deployed in our university's course. Then we also provide an API to get the extracted text. That's all.
Nice, Shangan. Could I ask, I don't know how Tesseract works internally, but can you talk about where in the code base are the models? Is it a per character model? And then which of those did you fine tune? And what types of models are they?
Yeah, actually, the Tesseract earlier versions are using regular neural networks, but we used the Tesseract 4 version, that is exactly the LSTM based models. So we get the LSTM based models from the Tesseract GitHub repository, then use that models to fine tune on the additional fonts.
Okay, and what's the input to the LSTM? Like what?
Yeah, actually the inputs to the LSTM is the TIFF text file. So initially we have an sample text in a text file. Then we used those texts to produce TIFF files and the corresponding text file. So those are the inputs to the model. So then the model will automatically detect the characters in the text file, TIFF file, then match with the coordinates. From the coordinates file we inputted to the model. So then corresponding characters also fetched from the text file, then the mapping happens. I think I could share the repository with you for your reference.
Does the LSTM see the pixels of each character one at a time? Does it also see the coordinates of the characters or something else?
Sorry, can you pardon, please? Can you repeat, please?
Oh, I was asking, does the LSTM receive as input the pixels of each character or like the coordinates of the character or both?
Yeah, actually it's receive the coordinates of the characters, because before getting the coordinates, the model will transform the TIFF detected coordinate like pixels into the coordinates. Then the coordinates will map to the text character from the text file. But we didn't go internally during the fine tuning. So we just used the model and writing some script to process the TIFF text files and fine tuning. So we didn't try to change anything inside the model. Yeah.
Okay. Anyone else have questions?
Wait, so the model itself shouldn't take any coordinates or ground truth text, right? If it's just an OCR, it just takes a picture, output the words and coordinates.
Yeah.
So did you write the additional input in order to fine tune it?
No need. We only need to sorry. We only need to input the TIFF files and the text, but I think for the inference, actually happens what yeah, I think you ask for the processing inside the LSTM model or outside. I little bit confused.
I'm asking, well, the same question Jason asked, just which part of the model did you fine tune? And your answer was the LSTM, and I'm guessing LSTM is the part of the OCR, or is it all of the OCR?
No, it's a part of the OCR, but the part we fine tune is the coordinates, because the model comes with the coordinates file for all the characters for the particular language. If you take the Tamil trained model from the OCR Tesseract, it's have some characters, then the corresponding coordinates, special characters. Those are all kind of characters with coordinates. It has a file. So that file missing some coordinates that are related to the legacy fonts. Our part is identify the misdirected characters and find the accurate coordinates. Then we added to the coordinates file. That's what we did. But we created different samples with different font faces, different font sizes, and different resizing, like different pre-processing techniques we used to generate different types of like different type of visualization of a particular characters. That's what we did particularly, because a character can exist in different font size or different font. That's a problem. The model will fail to detect such ones. So that's the part we actually did.
Okay, I can ask more questions in Discord.
I have a question. Looking over the motivation slide, there's like an old form and a new form. It looks like it's comparing two ways of doing handwriting for these languages, which I'm guessing are Tamil and Sinhala. I guess I'm curious, is this like a shorthand? Like I'm trying, I don't know too much about these languages, but is this like cursive handwriting in the US? And then there's also this thing called shorthand, which people used to use, where they compress multiple words into one word for efficiency, but it was a lot harder to read.
Yeah, but in our language, these are the like that it is in the status of terminating, because the old Tamil writers or Tamil what do you call yeah, Tamil, mostly old Tamil writers use this language, these characters, but these days those characters are replaced by the modern words. That's the problem. But in the current,
I just searched Sinhala and I got all this really awesome calligraphy. So it looks like an old art form, and I guess that makes it a really hard ML problem. Anyways, I was thinking there's actually a person who is working on Japanese calligraphy, and she's been wrestling with some of the same issues. Like there's all these really specific characters that come up because it's a decorative language that makes it a particularly difficult problem to solve.
Cool. Great presentation, Sharangan. We should probably move on to the next presenter.
Okay, thank you.
Should be Emily.
All right, great. Cool. And I have way too many slides, so I'll just dive in. This is going to be about selection-induced collider bias, and it's going to be a case study in gender pronoun uncertainty. And I'll start with a motivational example. So we're asking the model to tell us what pronoun should go in the masked out token. So you may have noticed that in this case, the masked pronoun is co-referent with the psychologist, not the male patient. So I'll give you a moment just to read it. These sentences are intended to be tricky, and they're to test for biases in the model. So in this case, as humans, we know there's no way to predict the correct gender pronoun with any certainty given the features X. So, but most deep learning models are not afforded the privilege of saying that they don't know. So in this case, perhaps the correct pronoun is she, but there's no way to know this from the features alone. So this is a real problem in the ML community. It's all these papers we see here address gender pronoun prediction or pronoun co-resolution. And it's not just this specific scenario, though. Models are often asked to predict gender identifying labels from genderless features. An example is, translation, for example, from a more genderless language to a more gendered language. This last paper here added a new challenge data set to aid in this diagnosis. It's called the Winnow Gender Schema data set. And it's actually the sentence that we saw previously about the psychologist comes from this data set. So with such a tricky problem, why not just always use a gender neutral pronoun like they? That works fine in this case. The psychologist told the man to fill out the questionnaire so they, the psychologist, can make a preliminary assessment. But it doesn't always work. In this case, the sentence is a little bit different. Now, the psychologist told the man to fill out the questionnaire so blank could be quickly assessed. So now we know the gender of the person for the masked out pronoun, it's he. So using they now change the semantics of the sentence. It changes it from a single person to now maybe multiple people. So in this case, we do have gender identifying features in X. So we should use the pronoun predicted by the model for Y, he. So we saw an example of like an underspecified and well-specified learning task in those prior slides. And we claim that all learning tasks can be partitioned into those that are well-specified and those that are underspecified. Where we define a learning task as underspecified when none of the features are causes of the labels. So a single prediction task may be partitioned into those portions that are well specified and those that are unspecified subtasks. So for example, in the green task here, the part of speech tagging is well specified. Like the model's done a good job recognizing the fact that it should be a pronoun. The only underspecified part is which gender the pronoun should be. So wouldn't it be nice if a model could recognize that it's been asked an underspecified question and report its uncertainty about the prediction task when delivering its prediction? So I think much of the criticism that ChatGPT has received could be addressed with such a solution. In this case, for example, if we could recognize task uncertainty, then we could develop a heuristic for this particular problem such that the model will return they when uncertain and the pronoun prediction when certain. So we claim that we've done just that. By applying causal inference, and we've developed an open source demo where you can try this for yourself on many pre-trained large language models using any of the Winnow Gender Schema challenge set sentences or your own test sentences. But just getting ahead of myself, I'm going to skip really the slide. It's too much. This is what we claim are our contributions, but specifically, more important than saying it is showing it. So we demonstrate these methods are reproducible, they're super lightweight, they run at inference time, plug and play compatible with almost any BERT-like model, and we should probably send it to GPT too. We provide these open source demos, which I can link to later. So specifically in here, I'm gonna go through these items as much as I can. So I'll start with the beginning one, which we've already done a bit of, which is to cast this problem as a causal inference problem. And so here, causal inference is really just saying, what is the data generating process? What caused the data to appear in our data set? So in this case, the features in the data set, what's in the data set is just X and Y. And these symbols are up here are what we say are plausible causes of maybe how those features and labels got into the data set. So X and Y are the high dimensional features in the data set, and W and G are symbolic. And specifically, we'll get into it. So specifically, G is a cause of Y. W is a cause of something in X, and S is this selection node between the two of them, such that where S is equal to 1 for samples in the data set and 0 otherwise. So here I'm gonna I was like seeking out data generating seeking out variables W and G that fit into this particular relationship. Here, I settled on these in particular, but I would say it's a more general problem. I try to show that in the end that it's a more general problem, but gender pronoun resolution is a really easy thing to test in large language models. So these are the ones that I come up with here. So just an example of this WS relationship is, for example, in Wikipedia or sources written about people, it's plausible that this axis variable, which we'll call S, has become increasingly less gender dependent as W date approaches more modern times, but not evenly through all countries, through all places. And similarly with Reddit, we can say that maybe even in gender neutral hobbies or gender neutral subreddits W, the style of the subreddit may result in gender disparate access. The style of moderation, I meant to say. So now let's get into our demos. So first, we need to kind of like, mathematically motivate how we can measure this probability distribution of the labels given the features P of Y given X, and justify that is related to this assumed relationship of P of G given W, this assumed relationship between G and W that's induced by S. So here is what I claim the mathematical proof. So that gets us to where we are right now, but a problem is this really a gender neutral sentence? So in order to have an underspecified task, I claim that X has no features of the label in it, no causal features. And is that true in this case? I mean, I think we know, like in society that we live in, like it actually, occupation is gendered, and that while that's changing, it's not at parity. So what we would like is a sentence that is really strongly genderless. So we had to develop our own, did I skip a slide? Oh yeah, so sorry. We developed our own data set to do so. And you can just imagine this is the data set. So we have these really genderless sentences, like about people just existing in space and time. So we used a heuristic to develop this data set. And time-wise, where am I at? Okay, so I'm just gonna like show, so there's correlation. We show it on these we claim genderless texts. And you could play with the demo yourself and get some intuition for that yourself. And I think interestingly, this is super anecdotal, but I see it in ChatGPT as well. So here ChatGPT, it does similar. With earlier dates, it's more likely to say he. With later dates, it's more likely to be like uncertain, like I think is an example, a fine example of they or uncertainty. And we see similarly, this is the demo that you could try out for yourself, this exact same sentence given to Bert, I think in this case, as we get to more modern times, 2001, the softmax probability for he and she is very similar, but in 1801, there's no doubt about it, it's 20% or 25% she, 60% he. So similar, perhaps similar pattern in ChatGPT. So we see the same thing with gender and place. So I'm going to move ahead to this uncertainty demo that I discussed earlier. So in this case, we took the Winnow gender evaluation schema and we added a little bit of extra data to it to make it that some of the sentences are well specified. Basically, yeah, it's not super interesting, but we added man and woman to describe the participant, because we're previously in the schema to challenge models, all of them are underspecified. And we also did our technique of injecting this date into it. The idea being that, let's see, so the idea being that if the model is so desperate for features that it's clinging on to this really weakly associating date feature in order to make a prediction about gender, we claim that model, that prediction task is underspecified. And what you can see here that's kind of interesting. So this shows the plots that we saw before, but for now, these sentences that come from the Winnow gender scheme are not our own genderless ones. And what is interesting is that, so a couple things. So I think what's interesting is that if you just look at a single time here, like let's look at like 1960, then we see the gender bias that's been known between like occupation and gender. So just for example, like if we look at the sentence, number 4, the doctor told the patient that Mask would be on vacation next week. So in this case, the masked out pronoun is referring to the doctor, with the one in bold. And if we look at sentence number 4, that's this blue one. And in 1960, like the model's quite certain it's a man, because this is the prediction, this is the softmax probabilities for women. So 1960 for sentence 4, the model's quite sure it's a man. Look at the version of that where the pronoun's co-referent with the patient, number 8. the doctor told the patient that mask would be at risk without the vaccination. So in this case, the masked out pronoun is co-referent with the patient. That's sentence number 8. So here's sentence number 8 in 1960. The model's less certain. A patient can be a man or a woman. In 1960s, the model's okay with that. Only in 1960s, the model not okay with the doctor being a woman. So we see this gender bias along this dimension, but what we've added is we also see this gender bias along the time dimension, and they roughly appear to be additive. I mean, it's not perfect, you know, the slope is maybe flattening a little bit, but roughly the two biases are combining. And importantly, also what we see is that in the well-specified sentences, so in this case, that's only 7 and 8. So 7 and 8, we know, no, sorry, 5 and 6. And 5 and 6, we know the gender of the patient is a man or a woman, and it happens to be co-referent with the masked out pronoun, unlike 1 and 2, where the masked out pronoun is co-referent with the doctor. So only 5 and 6 are well specified. Like as humans, that's the only one we would know for sure what the gender is. And you see 5 and 6 right here, 5 and 6, this is 6, this is 5. Those are the only ones where it's flat. So all we do is we look at like the super simple heuristic. You can do a lot more sophisticated stuff. We just look at the delta between like the average of these softmax probabilities minus these. And we just subtract them, and you can see that across all the models, using this heuristic, there's much we see low certainty for the well-specified ones and high certainty for every other one, which is appropriate. That's how humans would be as well. If we like make an artificial cutoff, okay, cool. If we make an artificial cutoff of like 1.0, then like we would have 100% accuracy. So now just doing that across all the different occupations, we see, this is where everything's underspecified in all these examples. We see higher uncertainty. In these two cases here, this little upright purple and horizontal green, across all the different occupations, we see uncertainty being reported as 0, more often than not, appropriately. In this case, like 90% of the time, the model's correct, even on these tricky sentences that I have to think about. So really quickly, we kind of claim that we can generalize this. We don't just have to have gender and genderless features. We basically just say that G are the causal parents of Y, Y are the non-causal, G are the causal parents of Y, W are the non-causal parents of Y, but they're included nonetheless because of the special relationship between X and S. So namely that W is a cause of X, and also W and G are both causes of S. And you can kind of test for this. We claim by, you'll see in a second by just basically plotting it out. So here, this is super simple. It doesn't look simple, but this is a super simple structural causal model, like basically data generating process that satisfies these two DAGs. And we show basically like empirically like plots that support what we showed on the large language models. So here we just see the correlation flipping only for the green, the underspecified one. And we see like, so here we see the correlation flipping when we flip this plus here, column I and in column double I, and we don't see it flipping for the well specified, which is in blue. And here we kind of see that effect of W injection as we increase this path of the strength of this path here. This is the equivalent of injecting the date into the text. We see that we can take something that was previously uncorrelated and make it well correlated. And we have these demos. And that is all.
Cool. It's been really cool to see this work evolve over the several research jams now.
Yeah, thank you.
I wish we had a lot more time. Does anyone have any questions for Emily?
I saw that you played with ChatGPT also on this task. How did it do?
Yeah, so I really had to like kind of pin ChatGPT in a bucket because it was much more creative. So for example, I had to say here, like specifically use a pronoun, which is, I don't know, feels a little unfair. I was really forcing it to just use a single pronoun, but it did similarly, honestly, to Bert, which is surprising. It does still seem to have, there does seem to just be this correlation, spurious correlation between date and gender. You know, I mean, it's plausible, it's understandable, but yeah, it is, it seems to still have it. Though not as much. I mean, I would definitely sometimes get she, you know, I probably tried this like 6 times, and some of the times I would get she. I'd also get like George Washington. I'd get weird stuff.
Also just through reading prompts a lot. Seems like when referring to year, a time, those language models likes a form when you say the time is 1821 instead of in 21. You are a language model.
Oh, interesting.
Just anecdotal, but seems like they like those prompts better, but who knows?
Yeah, and I mean, I think that's a really good point. So I think they're so sensitive to the prompt, particularly when there's no good feature of the desired label in the prompt. I mean, I remember when I was working on this, developing this data set, I would see differences if I had a comma or not. Like it was so sensitive. You know, I think other works has found even like the random seed can change this. So ultimately, like each data point here is an average of like 60 of these types of sentences. So try to address that sort of sensitivity.
We're a bit over time, so maybe we should go on with Stephen. Last
Thank you.
presentation. Emily, I have more questions, but I'll ask you on Discord.
Okay, fabulous.
Hi everyone.
Hello.
Yeah, I'm trying to share my screen right now. Okay, great. So I once again, Steven. I'm an independent researcher, mostly within a collective, and I'm also a computer science on my final year from Nigeria. Yeah. So I'm scheduled to finish in a few months' time, and I sort of started looking for my interest shifted a little bit to ML efficiency. So I started looking for topics I could do in that regard. You know, I was very eager about changing my undergrad thesis. Yeah. So I came up with this, and then yeah, I just want to share about my ideas, and then steps that I could possibly take moving forward. So I stumbled upon this picture, and apparently is a piece of antique. Yeah, it's a ML engineer fine-tuning an early version of SQLs, maybe 8080s, and this sort of make me a little bit more appreciative of how far um, how far we've come in efficiency machine learning generally over time. But unfortunately, the picture is not real. So yeah, this is a joke. Okay, so I started looking at composition techniques in machine learning generally. You know, especially we have large language models, and trying to deploy these models in deploy these models in real life environments could be a challenge at times, not just in maybe particularly on resource constraints environments. So I started looking at ways by which this was being mitigated, and I came across neural network pruning generally, and apparently that's like a method that I used to reduce the number of parameters in the train network. Yeah, and that can help reduce the storage requirements and improve the speed of inference without sacrificing accuracy. But usually it is difficult to train a network from the start with a sparse architecture. So this work, lottery ticket hypothesis, suggests that there are subnetworks within a dense, randomly initialized network that can be trained in isolation and can be trained to reach a similar level of accuracy as the original network in a similar number of iterations. So yeah, so that's the lottery ticket hypothesis, and it presented an algorithm to identify those subnetworks, and initially those subnetworks can perform at similar or faster accuracy, you know, with less than 80% or 70% of the original size of the network. Yeah. So so those smaller subnetworks are known as they are known as the winning tickets, because there's like there's like there's like an initialization lottery which they are winning, and then that makes them particularly effective when doing them, offer the same and offer same tunability, expressiveness, and transferability skills, you know, as the original network. Yeah. Okay, so and this also means that this, oh, sorry. Okay, so this means that, okay, what was I going to say there? Okay, so initially the accuracy of the winning ticket when compared to the original network, uh, it was discovered that the winning ticket could perform at similar accuracy or at an accuracy that exceeds the accuracy of the original network. So, which means we're saving a lot we're saving a lot on the efficiency side, inference or model size and deployments generally. And this could be a big win when utilized in a resource constraint on environment. And apparently this work has this work was like, should I call it a revolution in the ML efficiency space, So we've had like lots of works, that sort of depend on this particular work. So apparently I saw that there's more than 2,000 citations already. I mean, within I think 3 years, yeah. And I think that's very impressive. And it shows how important the work might have been in the field of ML efficiency. Yeah, but there are a couple of problems with trying to use sparse models with a focus on lottery ticket hypothesis. So I I tried using ChatGPT, earlier last week. So yeah, this was one of the questions I asked, and apparently training in many situations the performance of the neural network is dependent on the interaction between its different components, and removing or training a subnetwork in isolation could might not yield the same result. And then also there's the issue of trying to find the winning subnetwork in a large or complex system when the training data is extremely noisy. And finally, the lottery ticket hypothesis might not take into account the generalization performance of a network, which is the ability of a network to perform well on unseen data. Okay, so but I've been reading a lot in that field, like trying to understand possible problems. There's this phrase that I came across recently, which is can we win everything with a lottery ticket? So and one thing I discovered during my literature review is that accuracy might not be the only reliable measure of the model performance, and then we might have more complicated performance dimensions than just the tested accuracy, and that leads to issue including generalization to distribution shifts, which I mentioned earlier. So it was discovered that it's very while using pruning, it's very easy for the model to be what's the word? It's very easy to experience something like um imbalance, I mean class imbalance, yeah. And then it might not really generalize very well to unseen data. And there's the issue of less confident prediction, and finally interpretability might be an issue because it might be harder to understand how the model is learning to predict. Yeah, so I included some reference here. So apparently I think Serahuka raised the first issue in 2019 about fairness in about the ability of the model to what's the word? The ability of the ability of the model to perform extremely well in regard to fairness. Apparently, compression might amplify existing algorithmic bias on the underrepresented long tail of a data distribution, right? Which is at odds with fairness objective, obviously. And there's the robustness issue. In terms of robustness, the author sort of mentioned that they sort of mentioned that compressed models might be more sensitive and brittle to shifted data distributions, such as naturally corrupted samples. And in terms of privacy, I think compression uh, pruning performs extremely well in that regard because usually we are like using a segment of the entire model architecture, which means that even though the data was trained on all the networks, on all the parameters, we are using just a selected number of parameters, which if we try to invert the training data that was used to train the model, we might not get the full picture. of the training data. So this is not necessarily an issue for sparse models. And then the final one is uncertainty. The final one is uncertainty, which is more about how confident the model is about its prediction. So it's been discovered that sparse models might be a little bit less confident in their predictions. So recently I had a chat with I had a meeting with Hossein Mobai, who is one of the authors for SAM, sharpness minimization. Thank you, Hossein, for that, by the way. So we had a very interesting conversation about optimization in ML generally, and then he mentioned this work, so I sort of checked it out. So the way SAM works is that SAM is an approach to improve generalization ability of a model. So it works by seeking parameters that have a uniformly low loss value in their neighborhood, rather than just the parameters themselves having a low loss values. So that way we have parameters that are that are robust to small changes, because it's taking into account the sharpness of the network prediction. So the sharpness is basically how confident the network is in this prediction, right? So, for example, a network that is very confident in its prediction will have a high sharpness, while a network that is less confident would have a low sharpness. So some sort of try to balance the network performance with its sharpness, and that is done by incorporating the term in the loss function that encourage the network to make sharp predictions. So that way we tend to have models or training that are sort of converge around the flat minima, right? Yeah. So, and the bigger effect of this on generalizability is that the fact that, oh, okay, sorry, thank you for that. Thank you, Jason. Yeah, so the bigger effect of that is that the fact that we have like we have a model converging around the fat minima. It means that
I think we lost Stephen.
Yeah, unfortunately.
Anybody want to improv the rest of his talk? All right, hopefully he'll reconnect.
Is that when some parameters are changed of the model, right? So
Yeah,
oh,
we lost you for a bit.
sorry about that. Yeah, I was almost done. I'm so sorry about that. Okay, so I was saying that Sam was like it has been a state of the art result for a long while. So it's sort of so I thought, that can the superior generalization ability of Sam be deployed to build a higher performing sparse models. So in that way, we can make sparse models generalize more effectively than they're currently doing, So I started outlining how I was going to work on this. Then I found this today. Yeah. So apparently there's a team in CMU who did something similar and published it at Carnegie Mellon at EMNLP. I mean, this year's EMNLP. I think it's still ongoing. Yeah, okay. I think it finished earlier this week. Yeah, so this sort of proved this work proved my question, right? Because it's made use of SAM to try and build models that could generalize better, because the models training sort of converge around the flat minima. Yeah. So obviously, I've been thinking about ways I could maybe build on the work, or do something that is adjacent to this, but I've not been able to think of anything yet. But if any one of you has a suggestion or thoughts on possible ways to expand on this work, or build on it, I'll be very happy to take those suggestions. Okay, thank you very much.
Cool. We're a bit over time, so we should probably delay questions on Stephen's talk to the Discord. But maybe let's thank all the speakers.
We'll do that.
And
So it's good to have your intuition be verified by other people, by an existing paper, right? So hope you don't feel bad about that, but instead feeling good about it.
Thank you.
so next we'll head over to Discord for individual kind of one-on-one or small group on one questions for the speakers. I pasted the link in the chat. Anything else, Roseanne, before we wrap up?
No, Happy New Year. Won't be seeing you guys until next year.
Yeah.
Mm.
All right, see you on Discord.
Happy New Year.
Happy New Year.